Hello everyone. In this video I shall cover the subtopic 5.4 of energetics, which covers the Born-Haber cycle. The Born-Haber cycle is an energy cycle constructed for ionic substances as stated here. So far in the previous videos or previous sections of this topic, we have discussed energy cycles that have been drawn for covalent substances. In this section, we will consider an enthalpy level diagram or an energy cycle constructed for ionic substances. Before we can consider the Born-Haber cycle, which is constructed for ionic substances, we must consider the definitions and the processes involved in the Born-Haber cycle. Some we have covered in topic 3 and 13. Which is periodicity, and two new definitions will be covered in this section as well. The first new definition is the standard enthalpy change of atomization, which is defined as the enthalpy change when 1 mole of gaseous atoms is formed from an element under standard conditions. Thus, the major points to look for in this definition is it's the enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state under standard conditions. This book lists some examples here. For example, if we got the element of hydrogen, which exists as H2 gas over here, the definition states it's the enthalpy change when 1 mole, as you can see here, 1 mole of gaseous atoms is formed from an element in its standard state. Thus, this should be multiplied by half to balance the equation. This might be confused with bond enthalpies, but I will cover the relationship between delta H atomization and bond enthalpies in a bit. They've used another example here, as Cl2 gas. Chlorine exists as Cl2 gas as an element, and to form 1 mole of gaseous atoms, we would have to multiply the Cl2 by half here. On the other hand, for a metal, it's simply the symbol of the metal, Na solid, because it exists as a solid, to produce 1 mole of gaseous atoms from 1 mole of an element. I've listed more examples over here to clarify this. Thus, for non-metals, some non-metals exist as gases, some at standard conditions or in their standard state. Some non-metals exist as liquid, and some non-metals exist as solids. Let's start with these two examples have already been covered here. I'll start with the example of bromine. Br2 exists as a liquid, and thus the enthalpy change of atomization, which is the enthalpy change required to form 1 mole of gaseous atoms over here, 1 mole of gaseous atoms from an element in its standard state. Thus, this should be multiplied by half once again, because we only require 1 mole of gaseous atoms. If you can notice here, this enthalpy change of atomization involves two processes. It would involve evaporating the bromine liquid into a gas initially, and then breaking its bond enthalpies. Thus, the atomization would involve two processes, which is to first evaporate the nonmetal into gaseous molecules, and then break the bonds between the Br atoms, which we defined as bond enthalpies last week, into gaseous atoms. But we only require 1 mole of gaseous atoms. In this case, Cl2 is already in the gaseous state, and thus the enthalpy change of atomization is the enthalpy change required when 1 mole. The enthalpy change when 1 mole of gaseous atoms, once again, is formed from an element in its standard state, which in this case chlorine is a gaseous molecule, and thus needs to be multiplied by half to produce only 1 mole of Cl. For elements, non-metals that exist in the gaseous state, such as Cl2 or H2 used here and here, there's a clear relationship between the enthalpy change of atomization and the bond enthalpy. Since the bond enthalpy definition is the enthalpy change when 1 mole of gaseous covalent bonds are broken under standard conditions, as displayed here. This is the definition of bond enthalpy for Cl2. Chlorine exists as a gas, and thus any energy supplied at this point would go to break the Cl-Cl bond and produce 2 gaseous atoms. But the definition of enthalpy change of atomization is to produce 1 mole of gaseous atoms, and thus there is a clear relationship between these two, since they exist in the gaseous state, and the definition of bond enthalpies requires the bonds to be in the gaseous state, in a molecule in the gaseous state. Therefore, in this case, if the Cl-Cl bond enthalpy produces 2 moles of gaseous atoms, while the enthalpy change of atomization produces 1 mole of gaseous atoms, and thus there's a clear relationship between the enthalpy change of atomization of gaseous nonmetals and bond enthalpy. The delta H atomization of Cl2 gas to produce 1 mole of gaseous atoms would also equal half its bond enthalpy, since the bond enthalpy produces 2 gaseous atoms, but the enthalpy change of atomization produces 1 gaseous atom, as seen here. And this only applies for elements in the gaseous state, since bond enthalpies are for bond enthalpies in the gaseous state, and thus this should be in the gaseous state. Therefore, this wouldn't work for Br2 liquid, since it's a liquid and it's not a gas. But the enthalpy change of atomization of Cl2 gas would equal half its bond enthalpy. The same applies for a hydrogen gas. The enthalpy change of atomization of hydrogen to produce 1 mole of gaseous atoms would also equal half its bond enthalpy. Or you could look at it as the bond enthalpy of hydrogen would equal 2 times its enthalpy change of atomization, and the bond enthalpy of Cl2 would equal 2 times its enthalpy change of atomization. We have some nonmetals that exist in the solid state, as seen here, as carbon solid, and thus the enthalpy change of atomization states that it's the enthalpy change when 1 mole of gaseous atoms is formed from an element in its gaseous state, and thus this would represent the enthalpy change of atomization of carbon. Therefore, one trick that students fall for is this that I stated here. You should always remember that the enthalpy change of atomization of gaseous elements, such as Cl2 gas, H2 gas, F2 gas, equals half its bond enthalpy, because the enthalpy changes of atomization are not listed in the data booklet for non-metals or metals. They will always be given in a question. Thus, if you were not given the enthalpy change of atomization of Cl2 gas, and it's not listed in the data booklet, you would have to use half its bond enthalpy to calculate its atomization. This only applies for elements existing in the gaseous state, such as Cl2 gas, H2 gas, or F2 gas. And this is what the book lists here. The value for the enthalpy changes of atomization of hydrogen and chlorine. The values for the enthalpy changes of atomization of hydrogen and chlorine are half the bond enthalpy values. And this works for hydrogen and chlorine since they are in the gaseous state, and it would work for any other nonmetal that exists in the gaseous state, such as F2 gas is another example, or O2 gas would work, or N2 gas as well. The bond enthalpy for Cl2, they state here, refers to breaking 1 mole of gaseous covalent bonds to produce 2 moles of gaseous atoms, as I stated previously, but the definition of atomization is to produce 1 mole of gaseous atoms, and thus the bond enthalpy for gaseous elements, such as Cl2 gas here, the enthalpy change of atomization of Cl2 would equal half its bond enthalpy. As for metals over here, metals exist in the solid state, as seen here, and thus their enthalpy change of atomization has no trick. The enthalpy change of atomization is the enthalpy change required to produce 1 mole of gaseous atoms from an element in its standard state, such as sodium solid here, or magnesium, from 1 mole of magnesium or magnesium atoms from magnesium solid, or 1 mole of calcium gaseous atoms from calcium solid over here. I would like to display the relationship as stated here between bond enthalpies and enthalpy change of atomization more clearly. Allow me to zoom it in. As you can see here, this cycle would clarify the relationship between them. It lists here Br2 liquid. So it's an element in its standard state. It's converted into 2 Br gaseous atoms. This is not the definition of enthalpy change of atomization, since the enthalpy change of atomization produces 1 mole of gaseous atoms. But since in this case you're producing 2 moles of gaseous atoms from an element in its standard state, thus this would be defined as 2 multiplied by the enthalpy change of atomization of bromine as stated here. This process involves initially vaporizing Br2 liquid, as I stated previously, into Br2 gas. And this arrow would represent the enthalpy change of vaporization of Br2. And once Br2 is in the gaseous state, any energy supplied after that will go to break the Br bond enthalpy to produce 2 gaseous Br atoms. I hope this clarifies the relationship between enthalpy change of atomization and the bond enthalpies. And in this case, I used a liquid to indicate that the process involves enthalpy change of vaporization. One thing you should note as well is that the enthalpy changes of atomization are all endothermic processes, whether it's for a metal or for a non-metal. They are all endothermic processes since they involve breaking bonds, as well as sometimes, if it's in the liquid state, vaporizing it into gas before breaking the bonds. And thus all enthalpy changes of atomization are endothermic processes as listed over here in the book. Delta H atomization is always endothermic, whether it's for non-metals or metals, it's always an endothermic process. Some other definitions that are involved in constructing Born-Haber cycles are definitions that we've studied or covered in topic 3, such as enthalpy changes, such as ionization energies of atoms, as well as their electron affinities. Let's revise these quickly. The first ionization energy is defined as the enthalpy change when one mole of electrons is removed from 1 mole of gaseous atoms under standard conditions. And thus, as you can see here, it's when 1 mole of electrons are removed from 1 mole of gaseous atoms to produce unipositive gaseous atoms. The second ionization energy is the enthalpy change when 1 mole of electrons is removed from 1 mole of unipositive gaseous ions to produce dipositive gaseous ions, 1 mole of dipositive gaseous ions. We've covered these processes in topic 3, and we studied that all ionization energies, whether they are first, second, third, or any other successive ionization energies, are all endothermic processes, as stated here. All ionization energies are endothermic processes because you require energy to overcome the attraction between the nucleus of an atom and its valence electrons, and thus energy is required to remove an electron from its valence shell, whether it's first, second, or any other successive ionization energies. As for first electron affinity, it's the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous atoms under standard conditions. And thus, as you can see here, the definition is when 1 mole of electrons is added to 1 mole of gaseous atoms to produce 1 mole of gaseous -1 ions under standard conditions. We've covered this in topic 3, and we stated that the first electron affinity is always exothermic processes, since any atom would accept an electron to release energy and become more stable, which is stated over here. The first electron affinity is exothermic for virtually all elements. It is a favorable process to bring an electron from infinity to where it feels the attractive forces of the nucleus in an atom, and thus energy would be released to produce a more stable ion. On the other hand, the second electron affinity is the enthalpy change when 1 mole of electrons is added to 1 mole of gaseous -1 ions to produce 1 mole of gaseous -2 ions, as we covered previously in topic 3. The first electron affinity is always exothermic, but all other successive electron affinities are endothermic, since adding a negatively charged electron to a negatively charged ions would require energy, since they would repel one another to form an unstable ion, and thus the process is endothermic. This is stated over here. The second electron affinity, or any other successive electron affinity, second, third, fourth, and fifth, are always endothermic processes, because it is an unfavorable process to add an electron to an ion which is already negatively charged due to the repulsion between the negative charges. This was covered in topic 3, and this was just a revision. One other new definition is the enthalpy, is the lattice enthalpy, which is for ionic compounds. As you can notice from the term lattice, which is the structure of ionic compounds, they have giant lattice structures. I will cover that in a bit. I've stated here that the values above that I have just discussed, the enthalpy change of atomization, the first and second ionization energies, first and second electron affinities, are all experimentally determined values, and thus they are accurate values, and they will be used to construct energy cycles known as the Born-Haber cycles. It's called Born-Haber, which are the family names of two scientists that came up with the cycle, for determining lattice enthalpies of ionic compounds. Thus, all these processes that were covered so far will be used in the construction of Born-Haber cycles to determine the lattice enthalpies of ionic compounds. Thus, I will explain now what is meant by lattice enthalpies according to this definition here. Lattice enthalpy is the enthalpy change when 1 mole, once again let me note these, when 1 mole of an ionic compound is broken apart, thus this is defined as breaking, into its constituent gaseous ions under standard conditions. They've listed an example here in the book, for example NaCl. Thus we have 1 mole of an ionic compound. Metal with a non-metal forms an ionic compound, and they exist in the solid state at standard conditions. And thus the lattice enthalpy is basically the amount of energy required to break these ions apart in the lattice structure to overcome the attractive forces between these ions and form and convert it into its constituent gaseous ions, as stated here, as you can see here. Thus, the definition of lattice enthalpy is basically the amount of energy required to break an ionic bond. The stronger the ionic bond, the greater the lattice enthalpy required to break the lattice structure apart into gaseous ions. When you first, you should always keep in mind that to break an ionic solid, you must convert it into gaseous ions and not liquid ions, since in the liquid state, the ions are still held together by attractive forces, but they exist in the liquid state. Once you supply more heat and totally overcome the attractive forces between these ions and convert them into gaseous ions, at that point you would break the ionic bond. And therefore it's basically the amount of energy required to break 1 mole of an ionic solid into its gaseous ions under standard conditions. They've listed another example here, ammonium nitrate, which is also an ionic compound. The bonding is between 2 polyatomic ions, the ammonium ion and the nitrate ion, and it exists in the solid state. Thus, it's the energy required to break 1 mole of an ionic solid into its constituent gaseous ions, as you can see here, is called the lattice enthalpy. Lattice enthalpy here is defined as the breaking of an ionic bond, but it can also be defined as forming an ionic bond from the gaseous ions. I've stated this example over here. The lattice enthalpy is defined as breaking in this definition here and in the data booklet as well. The values listed are for breaking an ionic compound, which is an endothermic process, and thus all the values will be listed as positive values in the data booklet. This process is listed here. It's when 1 mole of magnesium chloride solid is broken into its constituent gaseous ions, as you can see here. Basically the gaseous ions, or the ions in the gaseous state that make up the ionic solid. And this is defined as delta H lattice according to this definition over here, and this is an endothermic process, the process to break an ionic compound into its constituent gaseous ions. But one can also form an ionic compound. I can form MgCl2, magnesium chloride solid, from its constituent gaseous ions. In this case, this would be an exothermic process, and this in some books is listed as the lattice enthalpy of formation, which is the lattice enthalpy, which is the enthalpy change when 1 mole of an ionic solid is formed from its constituent gaseous ions. But the values in the data booklet are the lattice enthalpy for breaking 1 mole of an ionic solid into its constituent gaseous ions. The book lists a very important note here. You should always look carefully to determine whether the lattice enthalpy is exothermic or endothermic, and this depends on the direction of the arrow. If the arrow is pointing from the solid towards the gaseous ions, then this is endothermic lattice enthalpy. But if it were the other way around, pointing from the ions towards the ionic solid, as in this example over here, then this would be an exothermic process, because bringing two gaseous ions, which are highly unstable, together and forming attractive forces to form a solid lattice structure, forming a more stable structure, thus would release a lot of energy. And this is what they state here, as it can be defined in either directions, as either making or breaking of the lattice. Here in this example, it is defined as the breaking of the lattice and is an endothermic process because energy must be supplied to separate the ions against the attractive forces holding them in the lattice. If you wanted the opposite process, which is to form an ionic compound from its gaseous ions, that process would be an exothermic process. These definitions are the definitions that we would use to construct energy cycles in for ionic compounds, which are called Born-Haber cycles. I will cover these in the next video, video number 2, which is constructing Born-Haber cycles. Please move on and watch the next video. Thank you for watching.